being at this new session of ZORP. We have two speakers today, Stephanie Chan first and then Carlo Pagano. There will be a half-hour coffee break between the two talks on Gallertown, like last time. The link will be posted on the chat. It is also available on the link in the email you received if you're on the mailing list. Yeah, and so now let us start. I'm very happy to welcome Stephanie Chan from the University of Michigan, who will talk to us about the density of ramified primes.
Right, thank you for the opportunity to speak here. I'll be talking about, well, the title says the density of ramified primes, but this is really a talk about spins, a special type of quadratic residue symbols. And this is joint work with Giorgio Milovic and Christine McMickens. Okay, so spins were sort of first properly studied by Vivano and Wannes, Major, and Rubin. So given a number field K, I denote by the totally positive units by OK plus. And they studied in certain number fields, number fields that satisfy these two conditions. The first condition being that the extension K over Q is Galois. And K is totally real, and that all the totally positive units are squares. The second condition is that the Galois group is a cyclic Galois group. And the spin symbol, right, of a principal ideal and an element sigma in the Galois group, it's really just the quadratic residue symbol alpha on the ideal A applied with sigma applied. And alpha is chosen as any totally positive generator of the ideal A. Okay, so a priori, well, if alpha and A sigma are not co-prime, right? Then this quadratic residue symbol will be defined as 0. But most of the time, we'll be looking at where this spin takes either plus or minus 1. And we will not look at where it's 0. So the reason we have this first property P1 assumed on this number field K is that we need this property for the spin to be well defined. Okay, so in particular, the assumption that that all the totally positive units are squares ensures that we can, well, first we can take an alpha that is totally positive because under the assumptions, the narrow class group and the class group, the ordinary class group always coincides, and we can always pick a totally positive generator in a principal ideal A. And second thing is that because any totally positive generators differ by a square, or under this assumption, then if any two choices of alpha would mean that the spin still say the same, the sign of the spin still stays the same. So, right, so this is the sort of first definition of spins. So there are some applications of spin. So there are certain places where the spin sort of appears. So an example they gave was on the two-Selmer group of elliptic curves. So for some elliptic curves that satisfy some conditions, which they stated in their paper, but here I just give like one explicit example that satisfy those conditions. So given this particular elliptic curve E here, defined by this equation, they show that the dimension of the two-Selmer of E twisted by P, where P is a rational prime that splits completely in K, where K is taken as Q adjoint all the two torsions. And it's assumed that the prime, there's a prime ideal above P that has a totally positive generator congruent to 1, 1, A. Then under these assumptions, the two-Selmer rank is either 3 or 1, depending on the sign of the spin P sigma. So sigma here is a fixed generator of the Galois group of K over Q. So there are some applications of spins to two-Selmer group of elliptic curves. Then you might also expect that it sort of appears in class groups of quadratic fields as well. So Koelmans and Milovich has done some work on 16 rank of class groups of quadratic fields, where spins also naturally appears, and they studied some sort of distribution of values of spins in that sort of settings. So, well, the spin is just a quadratic residue symbol, right? So we might expect, well, if we now fix sigma to be a generator of the Galois group, then as you vary P over principal prime ideals, then you might expect that, well, there should be 1 half of the time and -1 the other half of the time. So in Friedlander, Reynolds, Maser, Rubin's paper, they show that this sorry, let me do this again. Okay.
We can also share your slides and flick through them for you if you have problems again. Just drop us an email with the PDF.
Yeah, thank you. Sorry about that. I think it's just lost connection.
Not at all.
Okay, yeah, so it's conditional on this conjecture on character sums. This conjecture is about saving, power saving when you sum over chi A over A, where you take an interval that is shorter than the conductor of the character chi itself. So there are cases where this conjecture is proved. So for instance, this conjecture is known for when, so we have a parameter eta here, where n is less than or equal to the conductor to the power of eta. So this conjecture is known when eta is greater than 1/4 as a consequence of the classical Burgess's inequality. However, when you take eta less than or equal to 1/4, this conjecture is still open. And for sums that start from m equals 0, this is a consequence of the generalized Riemann hypothesis for the L function Ls chi. So we'll sort of assume this conjecture throughout the talk when we will be given several results, and they sort of all depend on this conjecture and short character sums. So the sort of the precise statement of their result, right? They sum over spins over principal ideals P, right? For all norms, all principal ideals P with norm less than or equal to X. And they've showed that assuming that conjecture, you can get a power saving on the sum. Right, so this implies that the spin P sigma, well, fixing sigma and varying P, you get -1 and 1 each half of the time. And this result also still holds when you impose congruence conditions on the ideal P. And the proof uses Vinogradov's method of sums of type 1 and type 2. So from the known cases of the conjecture, right, by Burgess's inequality, it holds for eta 1/3, which is the parameter you'll get for when you which is a parameter you can get when you take K to be a degree 3 number field satisfying those conditions before. But when you take a number field of high degree, say for 4 above, then it relies on the conjecture on short character sums. So we know what happened when we have one spin. So now what if we take several spins? So instead of fixing just one sigma, we fix 2 elements of the Gauss group, sigma and tau. And we assume that sigma and tau are distinct and that they are not inverses of each other. Koymans and Milovich prove that the 2 spins, so we're fixing sigma and tau now, and we vary P over prime ideals. Then they've showed that they essentially are distributed independently. So the more general statement of what they proved is that if we take a subset of the Galois group that is not empty, and that if you contain one element, you cannot contain the inverse of the same element, sigma, then the product of the spin over this overall sigma in the subset you take H. Right, as we vary P, this product oscillates as long as you pick the sort of the right type of set H, which is when which cannot contain both sigma and sigma inverse at the same time. And they've also removed the condition that K is a cyclic field. So now, so their result still holds if K is not cyclic over Q. But they still have to assume, of course, that K is a totally real field and that all the totally positive units are squares, because we need that for the spin to be well defined. This is a more precise statement of their theorem. The case when the number field is of degree 3, and we essentially recovered the previous theorem by Friedlander minus Mazur-Rubin, because the only choice of the subset H, right, is the set that only contains one generator. So when n is 3, then it includes the previous theorem, but the new thing would be when n is greater than 3, then it sort of tells you that any two spins, as long as sigma and tau are not inverses of each other and are distinct, then they have to behave independently. So, right, so why do we have to impose this condition that sigma and sigma inverse cannot be in the set H itself? That is because spin p sigma and spin p sigma inverse actually satisfy some sort of reciprocity, quadratic reciprocity. So in Friedlander minus Mazur-Rubin's original paper, they've showed that if you multiply these two spins together, then you get the Hilbert symbol, alpha alpha sigma, at all places, taking this Hilbert symbol over all places dividing above 2. So it depends on this Hilbert symbol on at even primes. And this can be proved just directly from Hilbert reciprocity. So the reason that the two spins here are not independent is because this Hilbert symbol doesn't behave randomly in the same way as before. Okay, so if you want to treat spins that involve sigma and sigma inverse together, then we have to take into account this Hilbert symbol. So in our work, we study a case when we take the set H to be all the whole Galois group with the trivial element removed. So all non-trivial elements of the Galois group are in our set H. And we also extend this definition of spins to non-principal ideals. So previously, the two results I've mentioned assume that the ideals are principal. But now, instead of assuming that all ideals have to be principal, we assume that the class number is odd. So now, instead of taking alpha to be the generator, totally positive generator of a principal ideal, right? We now take this to be the generator of the principal ideal a to the h. So instead of a, we take a to the power of h, so that we can assume that we have a principal ideal to work with. But we no longer assume that a itself is principal. Well, as before, we still assume the the conditions that it has to be totally real, and that all the totally positive units are squares for this symbol to be well defined. So we now have this sort of more general, but only works for number fields with odd class numbers. And because if we have, if the class number is even, then we have a square ideal, and that's bad for a quadratic residue symbol, right? So we have to assume that the class number is odd, but we no longer assume that the ideal is printable.
Stephanie, why would it not be enough to just assume that the ideal has odd order in the class group and then take this H to be the order?
That would be enough as well. It's sort of just it's just in our case, it's easier to just work with all sort of all ideals in the field. But yes, if you sort of restrict to those with odd order, then you can also define something similar, but I guess you're, yeah, so it depends what you sort of want to do, but that's completely possible. Just in our case, we sort of assume odd class numbers so that we don't have to sort of restrict to a subset of ideals to work with, but that is a totally possible way to do it as well. Okay, so just to show you the fields, the properties of the fields we're working with. So here, P1 is is assumed so that we have a well-defined spin, just as before. And P3 as well is so that we have this general definition of spins. We also assume that the Gauss group is cyclic, and that the number field has odd degree, and that the prime 2 is inner in K. So P1 and P3 here is for the definition of spin, but P2, P4, and P5 are to sort of make our problem more approachable and just limit to a case where we can sort of state some formulas explicitly. So we can also reduce these conditions or restate these conditions in a slightly cleaner way. We can replace, we can remove the totally real and totally positive units, B squares, from the conditions, because this is sort of implied by these other conditions here. I've just replaced P1 and P3 by C1 and C3, and the remaining, you can show that these two sets of conditions are equivalent. Okay, so I will, so I'll now tell you what we've proved. Okay, so we're looking at the density of primes that satisfy this spin condition that all spins P sigma is 1 for all sigma, for all non-trivial sigma in the Galois group. And we look at this density of this set in the set of primes that splits completely in the number field K. So here, so the way I've defined F it doesn't change, doesn't depend on the choice of the ideal above P, because we're taking sigma over all non-trivial elements of the Galois group. So any ideal above P would would sort of work for this set. And a different way to view this, because, well, the spin is just a quadratic residue symbol. A prime is in F if and only if, say, so there are 2 ways to state this condition. One is when P sigma splits in K root alpha over K for all non-trivial sigma. Right, but there's also the other way to state it, which is to to fix a prime P and look at the splitting in the n-1 degree quadratic extensions, K root alpha sigma over K. And so we can either look at n-1 primes in this quadratic extension, or this 1 prime in this n-1 quadratic extensions. And as before, I take alpha to be a totally positive generator of the ideal P to a power of H. Okay, so I will write the density of A relative to B, A and B being sets of primes usually, as D in this as D here. And as I said, the goal will be to find a density of F in the set S. So if you look at the condition that defines F, right, you have n-1 quadratic symbols here, quadratic symbol conditions here to satisfy, then you might think that maybe 2 to the, so 1 over 2 to the n-1 might be a good guess, right? So if all the spins are indeed independent, as we vary P, then the density would be 1 over 2 to the n-1. But as I mentioned before, spin P sigma and spin P sigma inverse satisfy, they're related by this Hilbert, this product of Hilbert symbols over even primes. So this is not, true in general that they are independent. Okay, so just to show you like show you some numbers here. We found a formula for the density of F in S, and we can compare with the natural guess of 1 over 2 to the n-1. And you see that, well, if we take the ratio, then if we look at degree 3, then they are the same. Then you might have thought, oh, like maybe 1 over 2 to the n-1 could be a formula. But then if you look at higher degrees, this ratio isn't constant, or it's usually less than 1, but there are also cases where that is greater than 1. Okay, so just to give you some indicator of what appears in the formula, if we compare with the order of 2 in the multiplicative order in the multiplicative group Z mod n of Z mod n Z, then so if we just focus on cases where this order is n minus 1, so for example, n minus 1 for 3, n minus 1 for 4, and for 11, for 13, and for 19, right? You see that, this actually gives you a sequence of ratios that sort of converges to a half almost. So it's not a lot of data here. Of course, we can look at, we can try to compute more data, but there seems to be some pattern here. So I will now show you what the density actually looks like. So we have this formula for the density, and actually it depends on the order of 2 in the multiplicative group modulo k, with k being divisors of n. Okay, so it's quite a complicated looking formula, but if we just reduce this, or we just take a look at the case when n equals p, n being a prime, we can simplify the product, the constant s plus and s minus, and give them in the following formula. And in particular, when the degree, so when the order of 2 in the multiplicative group mod p is p minus 1, then we can get the following formula for the density of f in S. And it actually sort of converges to 1 over 2 to the p when we have large, when p is large. So when the degree is large, it actually approaches 1 over 2 to the p rather than maybe, I guess, a 1 over 2 to the p minus 1. So to get the density, we also assume the previous standard conjecture on short character sum. So the cubic case is unconditional because of Burgess's inequality like before. Okay, so I will try and give you some indications of how the order of 2 in multiplicative group mod p actually comes into the picture. Okay, so the way we do this, the way we prove the density of f in S, so we split this density into a product of 2 densities with, so the first one being density of f in this intermediate set R. So R now is the set of primes that the spin p sigma and spin p sigma inverse agree. And so to prove the first density in this product, so it is essentially a modification of the proof by Coleman and Leverage, because we are really looking at we are really looking at half of we're looking at n minus 1 over two elements of the Galois group, right? So for every pair sigma and sigma inverse, we only take one sigma to look at, and applying a modification of their proof, we can show that this first density is 2 to the minus n minus 1/2. So there are some differences. So there are some modifications required because our definition of spins isn't exactly the same as theirs, because we're taking p to the h. So we're taking p to the class number rather than just principal ideal p. But essentially, it's the same idea that follows through. That gives us that these spin symbols are independent, right, when we only take sigma, one of sigma and sigma inverse in each pair of non-trivial element in the Galois group. So the different thing here would be to obtain the density of the set R in a set S. So we are looking at how often spin P sigma and spin P sigma inverse agrees as we vary prime P. Okay, so to do this, we have to use, of course, like the Quadratic reciprocity comes into the picture, and we have to consider the behavior of alpha alpha sigma, the Hilbert symbol over on primes that divides 2. And so suppose I call this condition that spin P sigma and spin P sigma inverse agrees for all sigma. And well, suppose I denote this property as star here. So this property star holds if and only if the product of Hilbert symbols are 1 for all non-trivial sigma. And to make studying this product more feasible, we assume firstly, well, we assume that 2 is inert, so that there's only one term in this product. So we only take, we only have to consider the behavior of one Hilbert symbol. And assuming that the Galois group is cyclic, let us sort of simplify our arguments and make it more feasible to state a more general formula. And the reason that we take the degree to be odd is because we do not want to deal with cases where sigma is of order 2. So, for example, if we have a field of degree 4, then we will have an element in the Galois group of order 2, and so spin P sigma and spin P sigma inverse are always the same thing, so they're always equal. Well, this density D, the density of R and S is always 1, but then what we cannot deal with is, as in previous work by Koymans and Milovich, it's not currently possible to study the density of such spin symbol. Okay, so so now we look at the distribution of a Hilbert symbol. So we want to restrict our attention to something that is smaller. So the Hilbert symbol is when you restrict the Hilbert symbol to all primes, and then it factors through this group M4, which is the integer ring modulo 4 and modulo all squares. So the property star only depends on the projection of P into this into the group M4. And this group M4, under our assumption, this is always of size 2 to the n being the degree of the number field. And we can, and using standard results like Shorter density theorem, you can prove that the density of primes in each class of M4 are equal, so that so primes are equally distributed in each classes of M4. So now we only have to count the number of classes in M4 that satisfy the property star. And the density would be this quantity divided by 2 to the n. So we are now just looking at 2 to the n classes and checking if they satisfy the Hilbert symbol condition for all non-trivial sigma. So to do that, so under our assumptions, we can find a normal basis for M4. So we can find an element so that M4 is so that y. So we find an element y, and y sigma, the set of y sigmas would be a basis of M4. So any elements of M4 can be written as a product of y sub I, where now here I'm writing y sub I as y sigma to the I, where sigma is now a fixed generator of the Gauss group. Okay, so with this basis, we can write down any element in M4 in terms of y and in terms of these yi's. And because the Hilbert symbol is multiplicatively bilinear, symmetric, and non-degenerate, so we can find matrix representation A that represents this bilinear pairing. And so we're taking A to have entries in F2, and we take entries in 0 and 1. So the ij entry, when converted to plus or minus 1, then this is the Hilbert symbol of yi comma yj at the prime 2. And we can write down the Hilbert symbol in terms of A and the row vectors that defines the element in M4. So the idea is that we can convert this Hilbert symbol condition into, in terms of A and the upper shift matrix. And we can reduce this problem to this sort of linear algebra problem where we're taking, where we're solving and trying to count the number of row vectors here that satisfy this linear algebra condition. So instead of counting in f2 to the n, so instead of counting the row vectors directly, we count the number of polynomials over f2 modulo x to the n minus 1. And we try to count the number of polynomials that satisfy the linear algebra condition converted to this problem over polynomials over f2 modulo x to the n minus 1. Okay, so we're using this correspondence, and what we get is that the number of classes in M4 that satisfy this property star is the same as number of polynomials f, such that x to the n times f to the f of x times f to the 1 over x is either 0 or polynomial h of x. H of x is determined by sort of the correspondence between the polynomials and the finite, the field f2 to the n. And so to count, so we want to count the number of polynomials that satisfy this condition. So the first step, the first set B inverse of 0, we're looking at when x to the n times f of x times f to the f of 1 over x is equal to 0. And this is in the, we're looking at this modulo x to the n minus 1. So in other words, we can rewrite this as counting polynomials f, so that f and f times its reciprocal is divisible by x to the n minus 1. And we are counting the number of polynomials with degree less than n to the n minus 1, because we're looking at this quotient ring with quotiented by x to the n minus 1. So the reason that the order of 2 in a multiplicative group of integers mod n is because so to count the number of polynomials, it depends on the factorization of x to the n minus 1. And this factorization depends on the order of 2 in the multiplicative group of integers mod n. Okay, so for example, well, if we look at degree 3, then so if we look at some factorizations here, so we're looking at polynomials, we're finding polynomials f, so that f times f inverse is divisible by x to the n minus 1. And so it depends on, so we can factorize x to the n minus 1, and we can look at these factors and see where we can put them, how we can put them into f. So some polynomials, some factors of x to the n minus 1 are self-inverse, and some are not self-inverse. So, I mean, self-reciprocal, and some are not self-reciprocal. So x plus 1 is always self-reciprocal. X to the n plus x plus 1 is also self-reciprocal. So there's only, so for degree 3, there's only one way to put these factors into f. Because if you put one factor, then say x plus 1 into f, then it will also be in the reciprocal of f. If you look at degree 7, you now start to get factors that are not self-reciprocal. Then you have the choice to put, so for instance, you can put x cubed plus x plus 1 into f, and x cubed plus x squared plus 1 into f star. You can also do it the other way around, and you can put the first one in f star and the second one in f. So this gives you more choices of f, and this gives you more a higher count in this set. So to get a general formula that works for all n, we need this lemma, which is just proved by just a simple Galois theory lemma. The factorization for any n, this factorization in the polynomial ring f2x, we can get a general formula for the number of factors that are in this factorization. We can also get the number of self-reciprocal factors in this factorization. So here, for example, the first m factors, so f1 to fm, are self-reciprocal, but for f1, so for fm plus 1 to fr, these are polynomials that comes in pairs itself and its reciprocal. So the number of terms here and the number of r and m and r are determined by the order of 2 in the multiplicative group modulo k. So once we've done this counting properly, we can get the two constants we want s plus and s minus. And now these two quantities depends on all these decays of the order of 2 in a multiplicative group. And so we can, putting this back into our formula of d of f given s is s plus s minus over 2 to the 3 n minus 1 over 2. Then that gives us our theorem. And in particular, when we're looking at the degree 3 field, we have s plus is 1 and s minus is 3 from the factorization. Okay, and this is the end of my talk. Thank you for listening.
Thank you very much. Let's all thank the speaker by unmuting yourselves and clapping. Okay, and so we're taking some questions.